Welcome back to the Deep Dive. Today we are opening up a massive and I think a really exciting new chapter.
It's a big one.
It really is. For so long we've been deep in the trenches of stochastics, distributions, axioms. The real heavy-duty machinery of probability.
The foundational stuff, yeah.
Exactly. And now we're taking all that hard-won knowledge and applying it directly to the technology that is, well, basically reshaping our world. Machine learning.
It's the perfect transition, really, because for a lot of people, machine learning or ML, it sounds like it's purely an informatics topic.
Right. You think algorithms, you think AI, neural networks.
All of that. But if you strip away the branding, the fancy software frameworks, what you're left with at the core, it's just applied statistics at scale.
So all that work we did on maximum likelihood, density functions, probability theory.
That's the engine. We're just scaling it up dramatically to solve these massive real-world problems.
Okay, so let's unpack that for a second.
Yeah.
Because I think anyone who's been following along might be asking, why did we go through all that heavy lifting? Visu das alles. Why master variance and likelihood?
And this is the payoff. The value is immediately clear when you look at how ML actually works. Mathematically, learning is a really precise three-part process.
Okay.
First, you have data, obvious but critical. Second, you propose a model. That's just a mathematical framework, like a line or a bell curve.
A template.
A template, exactly. And third, you try to estimate the model's parameters, we call them theta, so that the model describes reality or, lets you make really good predictions.
So it doesn't matter if you're fitting a line to some noisy points or classifying millions of faces.
Yeah.
Underneath it all, it's the same stochastic framework we've been building.
Absolutely. And that gets us to what I think is the core philosophical difference between traditional programming and machine learning. This is a concept you just have to get right away.
In traditional programming, you're the architect. You write the explicit rules. If A happens, then do B. You're writing the instruction manual for the computer, line by line.
Machine learning just completely inverts that whole process. It flips it on its head. We don't give the computer the rules.
What do we give it then?
We give it two things: the raw data, the outcomes, and that mathematical skeleton, the model framework. The computer's job is then to reverse engineer the rules.
So it looks at the data and just figures it out.
It looks at the outcomes and optimizes the parameters, the theta of the model, until that model best explains what it's seeing. In essence, the computer writes its own optimal statistical rules.
And we see this everywhere now. Autonomous driving, quality control, medicine. You name it. But why? Why go through this complex inversion when we could just code it by hand?
Well, there are three really powerful reasons, and they all point to the limits of what a human coder can do. The first one is just sheer complexity.
The things that are super easy for us to see, but impossible to describe in code.
Precisely. Try writing a set of if-then-else statements to define a nose, or a smile, or a cat. The variation in lighting, angle, shape. It's just impossible for a human to write down all those rules.
But a learning system can.
A learning system looks at millions of examples, optimizes its parameters, and implicitly learns that incredibly subtle, complex rule set.
Which immediately brings up the problem of scale.
And that's reason two, data capacity overload. Think about a modern physics experiment or weather prediction. You're talking about hundreds of terabytes of data a day.
A fire hose of information.
A flood. Millions of measurements from sensors, satellites. No human and no rigid, classically coded system could possibly handle that in real time. But an algorithm trained on stochastic patterns, it eats it for breakfast.
And the third reason, which to me feels like the most important for the future, is adaptivity.
Yes. A classic program is rigid. It's brittle. If the world changes, if consumer tastes shift, or a factory supply chain changes the material,
You just have to go in and rewrite the code.
you have to manually intervene, redeploy the whole thing. A learning system, though, is dynamic. It's always processing new data. So if your taste in music shifts from jazz to hip-hop, the ML system sees that statistical change and just adapts its recommendations. That ability to adjust is the decisive advantage.
Okay, before we dive into the math, there's one more crucial conceptual pivot we need to make. In this world, computers don't get customer profiles or cat photos.
Yeah.
They only understand one thing:
Numbers, vectors, that's it. So every single piece of real-world information, no matter how complex, has to be transformed into this numerical language.
And that transformation can be a huge job in itself.
It's mandatory and it can be painstaking. You're looking at job applicants, you have gender, education, location, salary. All of that has to become a vector of numbers. Maybe male is -1, female is +1, location becomes geocoordinate, salary is already a number, which is nice.
So every object, every applicant, every moment in time, it's just a single point in what could be a very, very high-dimensional space.
Exactly. So we're shifting our stochastic lens now. We're moving from the univariate random variable, which spits out a single number, to the multivariate random variable, which spits out a d-dimensional vector. That vector, we call it 6-sign, is one realization.
And the job of machine learning is really the study of these high-dimensional clouds of points.
That's the whole game. We're either trying to define the shape of those clouds, which is density estimation, or we're trying to find surfaces that perfectly separate those clouds, which is classification.
So let's formalize this. A model is a mathematical formula with these set screws called parameters, or theta.
Could be the slope and intercept of a line, could be the mean and variance of a bell curve.
And learning is just the search for the perfect theta, the one that gives the best fit between the model and the data.
A systematic, rigorous search.
And this search happens in 3 phases. Phase 1 is training.
That's the heavy lifting. Optimizing theta with something like maximum likelihood. Fitting the model to the data until it's as good as it can get.
Phase 2, prediction.
Once theta is fixed, the machine has learned, we lock it down and apply that static, trained model to new data to get our answers.
And phase 3, where the human comes back in. Model selection. These are the hyperparameters.
Right. These are the high-level choices we have to make. Do I use a line or a parabola? How many layers in my neural network? These are choices that frame the learning problem itself.
And today, we're focusing on one of those fundamental pillars. Not regression, not classification, but density estimation.
It's all about finding where the data points clump together. Finding the underlying probability function that generated that cloud of data in the first place.
And we are starting right there, diving deep into the math that governs these probability clouds in multiple dimensions. It is the absolute bedrock for everything else that follows in ML. So let's frame the mission. For density estimation, we are given n observed vectors, capital X. And we make a huge assumption right out of the gate.
A foundational one. We assume they are independent and identically distributed, IID.
Meaning they all come from the same unknown pot, the same density function, f.
And our goal is to find that f, or, get a really, really good approximation of it, which we'll call f hat. But the challenge is immense. The true f could be infinitely complex. Imagine trying to map every single ripple on a d-dimensional mountain range.
But we only have a finite sample of points, and we can't see the whole landscape.
We just don't have enough data to capture every little detail.
I have to jump in on that ID assumption. In the real world, things like financial markets or sensor data, that assumption gets broken all the time, right? Today's stock price depends on yesterday's.
That's a critical point for anyone thinking about applying this, yes. If the ID assumption is grossly violated, these simple models will fail you. You'd need to move to more complex tools like hidden Markov models or recurrent neural networks, things that explicitly model that time dependency.
But for today, to build the foundation, we assume independence.
We have to. So given this complexity, we need a way to make the problem solvable.
How do we do that?
We use something called parametric density estimation. Instead of looking for any possible function, we make a huge simplifying assumption. We decide on the family or the template of the function beforehand.
We say, this data looks like it was generated by a bell curve. We fix the shape.
You fix the mathematical shape, and our job is suddenly much easier. It's reduced to just finding the right parameters, the theta that fit that specific template to our data.
And the absolute classic, the most fundamental template there is the multivariate normal distribution. The bell curve, but in d dimensions.
It's the workhorse of classical statistics in so many ML algorithms. And while the formula looks a bit scary,
it does.
Its structure is actually very similar to the 1D Gaussian we all know. Our parameter vector, theta, is now made of 2 complex parts instead of just a mean and a variance.
Part 1, the expectation vector, mu.
This is a vector with d components, and it just tells you the location. It's the mean vector, the center of gravity. It's the summit of the d-dimensional mountain. It tells you where the data cloud is.
And part 2, and this is one that really defines the geometry, the covariance matrix, sigma.
Right. Sigma is a d by d matrix. And it has to be symmetric and positive definite. The positive definite part is just a mathematical constraint to make sure it's invertible and the density is always positive. But what it does, it determines the shape, the spread, and the orientation of that Gaussian cloud.
And looking at the formula, where in the 1D case we divide by sigma squared in the exponent, now we're multiplying by sigma inverse, so it's all linear algebra now.
The best way to get a feel for it is to visualize the simplest case, the bivariate case where d equals 2. If we have the standard normal, summa is the zero vector and sigma is the identity matrix.
Just ones on the diagonal, zeros everywhere else.
Then the distribution is perfectly symmetrical. The contour lines, the lines of equal probability, are perfect circles.
But the real world is rarely perfect circles. The moment you get some dependency, those circles get distorted.
And that's where sigma tells the whole story. The components of the matrix are everything. The diagonal elements are the individual variances, v of I1, v of I2, and so on. They measure the spread along each axis. If v of I1 is big, the cloud is stretched out along the by 1 axis.
And the off-diagonal elements, those are the covariants.
And that's where the magic happens. They capture the dependencies. If the covariance is not zero, the dimensions are correlated. And geometrically, that's what makes the circles rotate and turn into tilted ellipses.
This is where we need to connect it back to linear algebra. The shape and the tilt of that ellipse aren't just random, are they? They're defined by the eigenvectors and eigenvalues of the covariance matrix itself.
That is the big aha moment. It connects everything. The eigenvectors of sigma give you the primary axes of the ellipse. They tell you the exact orientation, the exact tilt of the cloud.
Are the eigenvalues?
The corresponding eigenvalues tell you how much the cloud is stretched in those directions. A big eigenvalue means a lot of variance along that main axis. So these two parameters, mu and sigma, they give you a perfect description of the location and the complete shape of the data cloud.
So we have the model template. Now, back to the learning problem. We have data. We've assumed the model is a multivariate Gaussian. We need to find the maximum likelihood estimators for mu and sigma.
And what's so nice is that the ML estimators turn out to be beautifully intuitive. For the mean vector, mu hat, it's just the average of all your data vectors. It's the geometric center of gravity, the centroid of the data cloud.
Simple enough. What about the covariance matrix, sigma hat?
This is where a concept called the dyadic product is central. The formula tells us to take the deviation of each point from the centroid, that's the vector, is the xm, and multiply it by its own transpose.
Okay, hold on. Let's clarify that. In one dimension, variance is just the squared deviation, right? You just square the number. What does this matrix multiplication actually do?
It's the generalization of squaring a deviation. When you do that outer product of a vector with its transpose, you don't get a number back. You get a full d by d matrix. And that matrix captures all the pairwise interactions, all the correlations between the dimensions for that one single data point.
And then we just average those matrices.
We sum up those matrices for all n data points and then average them. The result, sigma hat, is literally the averaged squared deviation, but in matrix form. It gives us the most likely shape of the cloud.
That seems very logical.
Yeah.
But this is the deep dive. We can't just accept the intuition.
No, we can't.
We have to prove it.
Mm-hmm.
And to do that, it looks like we need to roll up our sleeves and get into some pretty serious matrix calculus.
Right. We have to prove that the centroid and this average dyadic product are, in fact, the maximum likelihood estimators. So we start by setting up the log likelihood function.
Okay, so since the data is IID, the total likelihood, L, is just the product of all the individual multivariate Gaussian density functions.
And we immediately use the standard trick. We take the natural logarithm, ln of L. This is absolute crucial because it turns that horrible product into a nice manageable sum, and it pulls the matrix terms out of the exponent.
When you simplify it all down, the log likelihood, lnL, has three main terms. The first is just a constant with n and 2 pi. The second one is interesting. It has the log of the determinant of the inverse covariance matrix.
Yes, ln 2 ln textmo 1.
I want to pause on that determinant.
Mm-hmm.
Geometrically, what does the determinant of the covariance matrix even mean?
Geometrically, the determinant of sigma is proportional to the volume of the data cloud, the spread. A small determinant means the cloud is really concentrated and narrow. A large one means it's spread out. In the density function, it's basically a normalization constant to make sure the whole thing integrates to 1.
So maximizing that log determinant term is like encouraging the model to expand to fit the data.
In a way, yes, and that's balanced by the third and most critical term for the optimization.
The sum of the quadratic forms.
Exactly. Sum quando, sim one disin much. This part measures the squared Mahalanobis distance. It's the deviation of each point from the mean, but weighted by the shape of the cloud. So maximizing the log likelihood is really about minimizing this distance.
Okay, now for the calculus. We want the maximum, so we differentiate with respect to our parameters and set the result to 0. First up, the mean vector, mu.
For this, we need a recipe from the matrix calculus cookbook. The rule is, if A is a symmetric matrix, the derivative of a quadratic form WTA do with respect to the vector W is just $2, $8.
And our inverse covariance matrix, sigma inverse, is symmetric, so we can use this rule.
We can. So we differentiate the log likelihood with respect to mu. The first two terms don't depend on mu, so they just drop out. We're left with differentiating that big sum of quadratic forms.
Let's be careful here. We have to use the chain rule. The outer derivative, based on our recipe, gives us $2 sigma 1.
Right. And then the inner derivative. The derivative of Fixman mu with respect to 1 mu is, well, it's -1, or technically the negative identity matrix.
So let's track all the signs and factors. We had a -1/2 out front. That cancels the 2. The negative sign from the inner derivative cancels the minus sign from the differentiation rule. Wait, let's check the source materials convention here to be exact.
Good call. Looking at the derivation, the final result of differentiating that third term with respect to mu is actually sum nxn nn. The signs work out to give this form. And we set this whole thing to the 0 vector.
Okay, so we have the sum of sigma 1 equals 0. Since sigma inverse is the same for every term in the sum, we can just factor it out.
And here's the beauty of it. Since sigma is positive definite, we know its inverse exists and is invertible, so we can just multiply both sides of the equation by sigma, and poof, the sigma inverse term just vanishes.
Leaving us with something much simpler. The sum of xn equals the 0 vector.
Exactly, and we can split that sum. The sum of all the 6 vectors must equal the sum of the constant mu hat vector.
Which is just n times mu hat.
So n times mu hat equals the sum of all the x's divided by n, and there it is.
Hot mu frec 1n, some xn away. The proof is complete. The ML estimator is just the centroid, the simple average.
It's satisfying, isn't it? The math confirms the intuition perfectly.
It is, but now for the harder one. The derivation for the covariance matrix, sigma. This requires a different approach, doesn't it?
It does. If you try to differentiate directly with respect to sigma, the math gets, well, it's a nightmare. The smart trick is to differentiate with respect to the inverse matrix, sigma inverse.
Why does that make it easier?
It just linearizes the terms in a helpful way. Specifically, that log determinant term is much easier to handle. There's a standard identity for it.
So we need 2 new rules from our matrix calculus cookbook. Rule 1.
The derivative of that quadratic form, 2WTA, but this time with respect to the matrix A in the middle, is just the dyadic product ALUT.
And rule 2.
The derivative of the log of the determinant of a matrix A, so dull or more, with respect to A itself, is just the transpose of the inverse of A, so A1T.
Okay, let's apply these. We're differentiating the log likelihood with respect to sigma inverse. The first term with 2 pi is a constant, so it's gone. The second term was fracn 2 un 2 sigma 1.
We apply rule 2. That gives us fracn 2 times the transpose of the inverse of sigma inverse.
The inverse of the inverse is just the original matrix, sigma.
And since sigma is symmetric, its transpose is just itself. So that whole term differentiates to a very clean fracn sigma.
Nice. Now for the third term, the sum of quadratic forms. We're differentiating with respect to the matrix in the middle, sigma inverse.
According to our first new rule, that just gives us the dyadic product, x and mu, and we keep the -1/2 and the summation.
So putting it all together, the full derivative is sigma check-in 2, and we set this equal to the null matrix, the 0 matrix.
And from here, the algebra is simple. Multiply everything by 2 to get rid of the fractions, move the summation term to the other side. You get $1 hat sigma equals the sum of the dyadic products.
Divide by n, and we have it, the final result.
Hot sigma subs in hat mu.
So the math proves it again. The best estimate for the shape of the data cloud is the average of the quadratic deviations from the center. It's an incredibly powerful result. Okay, so the math for a single multivariate Gaussian is solid. It's precise, it's proven, but we have to face reality.
Yeah.
Real-world data is almost never generated by one single perfect bell curve.
This limitation is so important to understand. Our whole framework so far is built on this assumption of unimodality, one peak.
But what if the data is a multimodal? You imagine you're looking at cell activity, you see 2 or 3 or 10 distinct clusters of activity.
Right. And if you try to force our single Gaussian model onto that kind of multi-clustered data, what you get is well, it's a spectacular failure.
It's guaranteed to fail.
Absolutely. The maximum likelihood estimators have to compromise. The estimated mean, mu-hat, will land right in the empty space between the clusters, the point of lowest probability density.
So it picks the one place where there is no data.
Exactly. And the covariance matrix, sigma hat, has to stretch itself out enormously to try and cover both clusters, resulting in this huge, long ellipse that predicts high probability in a vast empty region.
So the model completely misses the point. It fails to capture the actual structure of the data.
The solution is to build a more complex model that acknowledges this underlying structure. We have to combine multiple bells.
Which brings us to the mixture distribution. The idea here is that we construct a new, more complex density function by just summing up a bunch of simpler ones.
Think of it like a sound mixer, right? Each of our component densities, a $50, is a channel, like a single instrument. And we have a volume knob for each one, which we call pick.
These are the weights.
These are the weights. They represent the probability that a data point came from that specific component, and they have to sum up to 1, so that our final mixed sound is a valid probability density.
When we use our trusty normal distributions for each of those components,
We get a Gaussian mixture model, or GMM, and this model is incredibly flexible.
because now each component, each little bell curve, gets its own set of parameters.
Each one gets its own location, muck, its own shape, sigmac, and its own weight pick. Our total parameter vector theta is now massive, but the model can capture these really complex multimodal structures perfectly. It can fit a nice, neat ellipse around each separate cluster.
A GMM seems like the perfect answer to this problem. So to get the machine to learn this massive set of parameters, we go back to our bedrock principle.
Maximum likelihood estimation.
We try to do the same thing again.
And this is where we hit an absolute immovable mathematical wall. It completely derails the analytical approach.
What's the problem?
The likelihood function for a GMM is the product of these mixture densities. And because the mixture density is itself a sum of different components, when you take the log likelihood, you end up with a mathematical nightmare.
What does it look like?
It's a sum of logarithms, of sums. You have
But
a
anyone who
GMM.
remembers their algebra rules, that's the fatal flaw. There is no rule for ln A plus B plus C.
None. There is no identity that lets you simplify that. You cannot pull the logarithm inside the sum. And that means the parameters for all the different components, all the mu's and sigmas, are hopelessly tangled up inside that log of a sum. You can't isolate them.
So all that beautiful matrix calculus we just did, it's useless here. We can't set the derivative to 0 and solve it. There is no closed-form solution.
Exactly. We're stuck. The direct route is blocked. We are forced to use a different strategy, a numerical iterative procedure. And this procedure is one of the most important algorithms in all of machine learning.
The expectation maximization, or EM, algorithm. So the EM algorithm is our way around this log of a sum roadblock. It's an iterative method. It's like taking a very careful hike up the log likelihood mountain with a guarantee that every step takes you higher.
The absolute genius of EM is how it handles problems where some crucial piece of information is missing. In this case, the missing information is which cluster did each data point actually come from?
We don't know the true assignments.
They're hidden. And to unlock the calculation, we have to introduce a new concept that makes everything work. It's called responsibility.
This sounds like the conceptual key. What is it? What is key F of X?
The responsibility, PFX, is a number that tells you how much component K feels responsible for generating the data point X.
Ah, I like that phrasing.
It's defined as the conditional probability that a data point X belongs to the K cluster, given our current guess for the model parameters, theta.
So if I'm a data point, it is telling me, based on where the bells are right now, what's the chance I came from bell number K?
Precisely. And if you look at the formula, it's just Bayes' theorem in disguise. The numerator is the prior probability of that cluster, pick, times the likelihood of seeing that point from that cluster's Gaussian. The denominator just sums those up over all clusters to normalize it.
And this is what allows for soft assignment. It's not a hard decision like in K-means clustering, where a point is 100% in or 100% out.
Exactly. EM is more nuanced. A point in the overlapping region between two clusters might be assigned 80% to one and 20% to the other.
Which is great because it quantifies the model's uncertainty.
It does. A point halfway between two bells will have responsibilities close to 50-50. And you see this in the visualizations as blended colors. It's a much more robust way of thinking about cluster membership.
This leads us straight into a classic chicken and egg problem, doesn't it?
It's the absolute definition of one. To calculate the best parameters, theta, we need to know the component memberships, the responsibilities. But to calculate the responsibilities, we need to know the parameters, theta.
So where do you start?
You start with a guess. You initialize theta with some random values, and then you iterate. You alternate between two steps until you converge.
Step 1 is the E step, the expectation step.
In the E step, we hold our current parameters, theta, completely still. We treat them as if they're the truth. And using those fixed parameters, we calculate the responsibilities, the circ values for every single data point and every single cluster. We are estimating the hidden memberships.
Okay, so we've colored in all the points based on our current model. Now for step 2, the M step, or maximization.
In the M step, we flip it. We now hold the responsibilities we just calculated completely still. We treat them as known, fixed weights. And using those weights, we calculate a new, improved set of parameters, thet and anew.
And there's a mathematical guarantee that this process actually works, that it makes things better.
There is. The log likelihood is proven to be non-decreasing with every single EM cycle. You are always climbing the hill. You are guaranteed to converge to, at the very least, a local maximum.
Let's dig into that M step. How do those responsibility weights transform the formulas we couldn't solve before into something we can actually compute?
By treating the FARC values as fixed weights, the partial derivatives of the log likelihood, when set to 0, suddenly yield these beautiful, iterative, weighted formulas. The weights basically decouple the parameters enough to solve for them.
Okay, so let's look at the update rule for the new mean of a cluster, mu-nu.
The formula is a weighted average. It looks almost identical to the simple ML estimator we proved earlier, but with one critical change. Every data point, xn, is multiplied by its responsibility, kuk, xn.
So if a point has an 80% responsibility for cluster K, it pulls the center of that cluster towards it with 80% of its weight.
Exactly. Points that are strongly associated with a cluster pull its center hard. Points that are weakly associated barely move it. And the denominator of that average is what we call n, the effective number of points in that cluster. It's just the sum of all the responsibilities for that cluster.
What about the new covariance, sigmic nu? The shape adjustment.
Same idea. It becomes a weighted sum of the dyadic products. We calculate the quadratic deviation of each point from the new mean, but we weight that whole matrix by the responsibility kxn. This lets the ellipse stretch and rotate to perfectly fit the points it's most responsible for.
And finally, the new weight, pinu. How big is this component in the overall mixture?
That's the simplest one. It's just the relative frequency. You take the effective number of points in the cluster, nk, and you divide it by the total number of points, n. If a component ends up being responsible for a third of the data, its weight will settle around 1/3.
Okay, let's walk through the whole cookbook recipe then, the full cycle.
Step 1, initialization. You have to start somewhere. Guess some starting values for all the mu's, sigmas, and pi's. A common way is to run k-means first to get some decent starting centers. Then you calculate your initial log likelihood as a baseline.
Step 2, E step. With those initial parameters fixed, you calculate all the responsibility values, you get your first set of soft assignments.
Step 3, M step. You take those responsibility values as fixed weights, plug them into the weighted update formulas, and compute a whole new set of parameters. The model literally shifts to better fit the data assignments.
And then steps 4 and 5. Check for convergence.
You calculate the log likelihood using your new improved parameters. You check how much it increased. If it's a big jump, you're still climbing steeply, so you go back to the E step and repeat the cycle.
But if the gain is tiny?
If the gain is negligible, you've reached a peak. You're done. You break the loop and output the final optimized parameters.
And you said this process is used all over the place, not just for clustering?
Oh, it's a universal tool. It's used in hidden Markov models for analyzing time series data think speech recognition, or finding patterns in sensor data from a factory, anywhere you have to infer hidden states from stuff you can only partially observe.
Seeing the algorithm in action really makes all this math concrete. Let's walk through the visualization of it learning.
Okay, so at the very start, the machine is completely clueless. The initial guess for the centers might be dropped randomly right in the middle of the empty space, and the covariance matrices are just simple circles. The initial log likelihood is terrible, very low.
Then we run the first E step. The points get colored in based on their responsibilities. Even with bad centers, the points closest to a given center get assigned to it.
And then comes the first M step, and this is where you see the first big jump. Based on those initial soft assignments, the center of gravity calculation immediately yanks the MUV vectors over towards the clouds of data they're responsible for, and the shapes start to distort from circles into crude ellipses.
After just 5 iterations, you can already see the structure emerging. The centers are in the right neighborhoods, the shapes are elliptical, but they're still a bit sloppy, maybe oversized or not tilted quite right.
But then you let it run. After 50 iterations, the system has converged. The model has learned the data structure with incredible precision. The ellipses are perfectly sized, rotated, and positioned to maximize the likelihood that this data came from this specific mixture. The machine has found the structure.
And we can track this by plotting the negative log likelihood. We want this curve to go down.
Right. And you see a very characteristic shape. A steep drop at the beginning. That's the gross positioning phase where the centers are moving fast. Then the curve flattens out. That's the fine-tuning, the little rotations and stretching at the end. When it's basically flat, the algorithm stops.
This whole process seems so elegant, but there's a huge, dangerous trap lurking here, specific to GMMs. You call it a singularity.
This is a critical warning for anyone who actually implements this. A singularity can happen when one of the Gaussian components becomes obsessive. It decides to focus all of its attention on a single data point, 6 eclipses. It means its mean, muck, collapses to be exactly equal to that one data point. And its variance matrix, sigmac, shrinks towards the zero matrix. It becomes an infinitely narrow spike.
What does that do to the math and the density formula?
It causes a disaster. The determinant of sigmac goes to 0. In the formula, we have the term 1 over the square root of the determinant. As the denominator goes to 0, that whole term shoots to infinity. And since the point is exactly at the mean, the exponential term is just 1.
So the likelihood goes to infinity. The algorithm thinks it's found the perfect solution.
A mathematically perfect but completely useless maximum. It has created this infinitely tall, infinitely narrow needle right on top of one data point. The model has perfectly explained that single point, but has zero ability to generalize its collapse. It's a pathological failure.
So the algorithm just follows the steepest gradient right off a cliff. How do we stop this from happening?
First, you have to know that this can only happen with mixture models, where one component can afford to abandon the rest of the data. In practice, we have to intervene. We use regularization. We can set an artificial minimum value for the variances, a floor that they're not allowed to shrink past.
Or if you detect that a component is collapsing,
You just reset it. If its determinant gets too small, you can reinitialize its mean to a new random point and force it to start over. You have to add these practical guardrails to stop the algorithm from finding these useless, extreme solutions.
that brings us to the end of a really dense but fascinating journey. We started with the philosophy of machine learning. We established the geometry of the multivariate Gaussian. We fought our way through the matrix calculus proofs.
Then we hit the multimodal problem and the log of a sum roadblock.
And we conquered it with the EM algorithm. We've really built the foundation for unsupervised learning, finding hidden structure in data without any labels.
That's right. The next logical step is to move from this unsupervised world into the supervised one.
Classification.
Yes.
Actively trying to separate the red points from the blue points.
Exactly. But before we finish, here's a final thought to chew on. The EM algorithm guarantees that we find a local maximum of the likelihood. We saw how important that initial guess is.
Right. If you start in a bad spot.
If you start in a bad spot, you might climb to the top of a small hill, but completely miss the giant mountain right next to it. Your final model could be just okay, not the best one possible. So what does that imply when we rely on these machine-learned structures for high-stakes decisions, like in medicine or finance? If we can never be 100% certain that the machine has found the absolute best model, is that a risk we're willing to accept?
An excellent and slightly unsettling question to end on. The inherent uncertainty that's still built into even our most powerful optimization tools. Thank you for joining us for this deep dive into the stochastic foundations of machine learning. We'll see you next time.